So, hello everyone who is watching on YouTube. So, I'll start the session in like 3-4 minutes since I'm waiting for a few students, for a few people to join the meeting. So, if no one joins in like let's say 5 minutes, I start the session. Okay, so since no one has joined the session till now, maybe I'll just start the session as it is for the YouTube audience. Yeah. So Yeah, for the YouTube audience, just to reintroduce myself. Hello, everyone. I'm Lakshya Saggi, the Discrete Maths NPTEL for the Tuesday sessions. So this is our 10th session, and like in this problem solving session, we'll be solving problems related to number theory and stuff. So basically, the stuff which you learned in this week. So yeah, I have set of like 5 questions prepared, and I'll start discussing these questions one by one. So yeah. So I'll just share my screen and then uh, I'll start just discussing the questions. So yeah, I'll just share my screen now. Okay, so I've started sharing my screen. So as you can see, this is the 10th session and like I have like 5 questions prepared for today. So we'll start discussing all these questions one by one. So just before starting discussing the questions, as I usually do in the problem solving sessions, I would like to Um, even if you have gone through the lectures, I'll just try to write some preliminaries which we'll be needing to solve the problems related to problems which are present in this problem sheet. So the preliminaries are generally the stuff which has been discussed in the previous weeks of the in this previous week, the weeks for which I'm discussing the problems. But yeah, I'll just be giving you a high level overview of what theorems we'll be needing. So yeah. So first of all, there are three primary things in number theory which you should know. So first is like Fermat's little theorem. So what is Fermat's little theorem? So Fermat's little theorem says that um, for any prime p, for any prime number p, so I hope you are. I'll assume that you are comfortable with the modulo notation and what's GCD of a number and like what does A mod B mean and stuff like that. Because all of this has been discussed in the previous weeks, like last 3 lectures. So I won't be discussing that, but I'll just be redescribing what Fermat's little theorem and then what Chinese remainder theorem state. So like it will be easier for us to refer to these theorems when we'll be solving the problems. So yeah. So for any prime number, so Fermat's little theorem states that for any prime number p, we have that for any prime number p and an integer a such that p does GCD of a comma p is 1. So what this means is a and p are co-prime. So for any prime number p and an integer a such that GCD of a and b is 1, maybe I'll just put this a as a variable. So I'll put it in italics. So it's easier for you to follow that this is a variable and not. Yeah. Such that GCD of a comma p is 1. Then a raised to power p minus 1 is congruent to. So generally, the congruency symbol is drawn with like 3 horizontal bars. But since I don't have 3 horizontal bar symbol in my keyboard, so I'll just be using this sort of symbol for congruency. This colon and then this equal to sign. So this is congruent to 1 mod p. So this is what Fermat's little theorem states. I'll just state where this symbol refers to the congruency symbol. So I guess this is for maths little theorem, and like it's not uh, too difficult to understand what the theorem states. It just states that for any prime number p and number a, which is like co-prime to p, a raised to power p minus 1 will be congruent to 1 mod p. So yeah. So basically, when this quantity a raised to power p minus 1 is divided by p, it will leave a remainder of 1. So yeah. And then what the second theorem which I'm discussing, which we'll be using, is the Chinese remainder theorem. And both of these theorems are like this format little theorem and this Chinese remainder theorem are like the central pillars for all of the number theory. So these are two of the most important theorems in all of number theory. If you ever want to pursue number theory further, these will be the stuff on which everything else will be based. So yeah, so these are sort of important. So Chinese remainder theorem is um, not complex, but rather a long statement. So I'll just give you guys what the CRT is. And let me just, I have an image from the lecture saved, which gives, okay, so yeah. So yeah, so I had this, I took this screenshot from the lectures, like what the Chinese remainder theorem is. So Chinese remainder theorem is like, it's also what CRT is. So let M1, M2 till Mn be pairwise relatively prime positive integers. So M1 to Mn are positive integers which are pairwise relatively prime. What does relatively prime mean? So basically like GCD of M1, GCD of Mi, Mj is equal to 1 for all I and j, which for all I not equal to j. So I hope everyone understands this pairwise relatively prime meaning. And so, and let a1 to an be arbitrary integers. Then the following system. So suppose we want to find out the solution for this sort of system where we are given that x is congruent to a1 mod m1, a2 mod m2 till an mod mn. So essentially what this means is that x minus a1 should be divisible by m1, x minus a2 should be divisible by m2 till x minus an should be divisible by mn. And then we want to find out the value of x, like what integer x will satisfy all these equations simultaneously. Then what Chinese remainder theorem states is that this system has a unique solution modulo the number m, which is like product of m1, m2 till mn. So if we multiply all these m1, m2, m3 till mn, we have this number capital M. So there will be a unique x. Like suppose we'll get an x which leaves the remainder, let's say k modulo capital M, and that k will be unique. So so what I mean to say is like any number which satisfies all of these equations will leave a unique remainder when divided by this capital M quantity. So this is what Chinese remainder theorem states. So this is sort of a very important theorem because like let's say there are just two numbers like M1 is 2 and M2 is 3. So this capital M will be sort of equal to 2 times 3, which will be 6. So what this essentially means is that if we are given two numbers, if we are given a number x, which leaves a remainder of a1 when divided by 2 and a2 when divided by 3, then any number which satisfies these two inequalities will have a unique remainder when divided by 6 also. So this is something which Einstein remainder theorem states. And another thing to notice that we would also like to find out, we are just given a property that this will have a unique solution modulo capital M, but we'll also like to find out what what the value of x actually is, right? Because we sort of always want to solve also an equation. So CRT also, as a part of its proof, CRT also gives us the value of x. So we'll not be proving because the proof why this value is true, but this proof has been done in the lectures. So you can refer to lectures if you would like to, but I'll just be stating what the value of x is. So if we define a quantity capital Mk as capital M divided by small mk, for k equals to 1 to n, where n is like the number of equations which we have. And then if we define a quantity small yk, which is multiplicative inverse of mk modulo small mk. So I hope multiplicative inverse is clear to everyone. What is a multiplicative inverse? Because this has been covered in the lectures also. So a multiplicative inverse is nothing but, so suppose we want to find multiplicative inverse of capital MK, then we just want to find out a yk such that yk times capital MK is congruent to 1 mod small mk. So basically multiplicative inverse is nothing but taking the product should have a value equal to 1 under the modulo symbol. Like not actually equal to 1, but under modulo symbol it should be 1. So I hope this sort of thing is clear to everyone. And we can sort of see that this yk will exist always, because this had been discussed in the lectures that if this capital MK and small mk are co-prime, then multiplicative inverse will always exist for capital MK. And we know that all these M1 to Mn are relatively prime, or like relatively co-prime. And because of that, this mk and small mk will also be co-prime. So that's why this small yk will always exist. Okay. So also we define like this mk is congruent to 0 mod mj for j not equal to k. And then what we claim is that the value of x will actually be equal to this. So let's just not think of this as a claim, but rather like this is actually the statement in Chinese remainder theorem, that this x equal to y1 m1 a1 till plus y2 m2 a2 till yn mn an. This value will satisfy this set of equations. Okay. So this will be one solution. So we have what we have claimed is that x equal to this will satisfy all these equations simultaneously. And because of this, as we know that this system has a unique solution modulo capital M equal to this value. So all the solutions will look like something like this value, this y summation of yi mi ai plus capital M times any number. Because modulo M, there is a unique solution. So if we keep on adding capital M any number of times, we'll obtain infinite solutions. But under like modulo capital M, we'll have just one solution, which can be found out by finding out this value, y1 m1 a1 till yn mn a. So yeah. So this is Chinese remainder theorem. So this looks a bit complex, but once you get the feel of it, and once we apply it in like 2-3 questions in the following sheet, then you'll get the hang of it, and it won't look so much confusing, or rather, yeah. So maybe I should just make it a bit bigger. Okay. Okay. Then maybe we can start with the questions, I believe. Uh, so, so the first question states, so for in first question, like it's just a match the following question, but rather like in the matching, we just have to find out these mod values. Like we have to, in the first question, we have to find 9 raised to power 210 mod 6. And like one of these will match to one of these options here. Similarly, in second part, we have to match 5 to the 5 to the power 300 mod 7. And similarly in third part. So we'll just go like part by part. So we'll just look at row 1 and find out this value, then find out second value, then find out third. So let's just do it part by part. So row 1. So row 1 is nothing but 9 raised to the power 210 mod 6, right? And we need to find out the value of this thing, this 9 raised to the power 210 mod 6. So generally, as we had already discussed, we have these two tools to work with. Primarily, we'll have just these two tools to work with And also we have the tool of finding the multiplicative inverse, which had been discussed in the lectures, which are called like Bezout's coefficient and stuff. So yeah, other than that, like mainly for finding out these modular values, we have these two tools. And as you can see, like for applying Fermat's little theorem, we sort of need the mod, the number for along which we are taking the modulo as a prime number. Like mod in Fermat little theorem, we need like mod p where p is prime. So here we have this 6 and 6 is not prime. So we can't apply a sort of Fermat's little theorem directly. But what we can do is like if a number is not prime, then it is composite. And if a number is composite, then we can write it in form of prime factorization, right? 6 can be written as 2 times 3. And if we write 6 as 2 times 3, then we can sort of apply Chinese remainder theorem instead. Because in Chinese remainder theorem, we see that this capital M is written as M1 times M2 till Mn. So if we take M1 as 2 and M2 as 3, then we'll have capital M as 6. And we'll obtain the required value. So I'm just putting this in on a very high level. I'm just giving you an intuitive idea of how to approach these problems. We'll just solve these properly instead. So we have to find out the value of 9 raised to power 210 mod 6, right? So maybe I'll just put row 1 here. Yeah. So what we'll do is let x be equal to something like this. Now we know that 6 is equals to 2 times 3. So we'll instead find the values. Instead of finding this 9 raised to power 210 mod 6 directly, what we'll do is we'll instead find the values of 9 raised to the power 210 mod 2 and 9 raised to power 10 210 mod 3. And why will this sort of thing be useful to us? Because let's say we find out this value 9 raised to power 210 mod 2 and then 9 raised to power 210 mod 3. Then we sort of have an x. Basically what I mean to say is we'll sort of have a number which when divided by 2 leaves a remainder of 910, 9 raised to power 210, like mod 2, and similarly, which leaves a remainder of 9 raised to power 210 mod 3. So when we divide it by this capital M equals to 2 times 3, we'll sort of have the actual remainder. Like we'll sort of have the actual answer which we want to find. So like this part of theorem won't be useful for us, the bottom part, but this yellow part will be useful to us. Maybe I'll just show you guys how. Um, so uh, what I mean to say is so we need to find something like this, right? That x is equals to 910 mod 6. So we can write this similarly as this also. Like this is an implication sign that we sort of need to find 9 raised to we sort of need to find 9 raised to power 210 is equals to x mod 6, right? And we need to find out the value of x here. So this is sort of the question. Like this question and this question are sort of same thing because these things in modulo symbol can be moved around. So this is a congruency symbol first of all, not exactly equal to symbol. So yeah. So yeah. So we can instead write that 909 to the power 210 is congruent to x mod 6 and we need to find an x, right? Similarly, here we need to find these values of 9 raised to power 210 mod 2 and 9 raised to power 210 mod 3. So what we'll do is let a equals to 9 raised to the power 210 mod 2. And what this essentially means is that uh, like we'll need to find out the value of a here. And what will be the value of a here? Uh, Maybe I'll just instead write down this only instead. So if we want to find out something like 9 raised to power 210 mod 2, uh, then we can instead write it as uh, like we know that this 9 can be written as 8 plus 1, right? So this can be written as 8 plus 1. Uh, okay, so yeah. Or maybe we can just say that, yeah. Uh, we know that 9 raised to power 210 mod 2, since 2 leaves, like we know that when 9 is divided by 2, it leaves a remainder of 1, right? So we know from the properties of modulo function, maybe I should write this in preliminaries also. Uh, like if A is congruent to B mod n, then A raised to the power k is congruent to. So this has also been discussed in the lectures, but I'll just be reminding you guys so that you guys can see what we are trying to essentially do. B raised to the power k mod n. So what this essentially means is that if I have something like 8 is congruent to, let's, so if we have like A is congruent to B mod n, then we can just raise the powers for on both sides. So that is what I'll try to do here also. So I know that 9 raised to power, and I want to find 9 raised to power 210 mod 2, right? So I'll just write finding 9 raised to power 210 mod 2. And for finding this, what I'll say is since 9 is congruent to, so I'll just apply this property directly. So we know that 9 is congruent to 1 mod 2, right? Because 9 leaves a remainder of 1 when divided by 2. So what this implies is that 9 raised to the power 210 is actually congruent to raised, since 9 is congruent to 1 mod 2, we can raise both sides to the power 210. So we'll have that 9 raised to the power 210 is congruent to 1 raised to the power 210 mod 2, which is nothing but equal to 1, because 1 raised to the power anything is equal to 1. So we know that 9 raised to the power 210 is actually equal to 1. Similarly, now finding 9 raised to the power 210 mod 3. Now this is easy because like we know, again, like you can directly see also that 9 when divided by 3, 9 is actually divisible by 3, right? So any power of 9 will also be divisible by 3. So this will just be equal to 0. But using these properties, like similarly, we can write this as we have done in the previous part also, that since 9 is congruent to 0 mod 3, this implies that 9 raised to the power 210 is congruent to 0 raised to the power 210 mod 3, which is actually equal to 0. So what we sort of essentially have is that we have that 9 raised to the power 210. Let this number be something like x, not x because we have x defined this x previously, but let this number be something like y. So when y is divided by 2, it leaves a remainder of 1. And when this y is divided by 3, it leaves a remainder of 0. So what we essentially have is that, so when 9 raised to the power 210 is divided by 2, it leaves a remainder of 1. And when divided by 3, leaves a remainder of 0, right? And this is actually similar to the Chinese remainder theorem, if you guys can see. So what Chinese remainder theorem says is that so let's say there is a number x which leaves a remainder of a1 when divided by m1, a2 when divided by m2. Then it will have a unique solution when divided by 2 times 3, right? And this is sort of something which we want, because uh, we have that the number when divided by 2 leaves a remainder of 1, and when divided by 3 leaves a remainder of 0. So when divided by 6, it will leave a unique remainder, and that is something which we want. We want the value of that remainder itself, right? We want this 9 raised to the power 210 mod 6 actually. So that's why we can sort of apply Chinese remainder theorem here. So essentially what we need to find is, so we need to find an x. Maybe I should not write this first statement. Yeah, maybe I should write something like this: to find 9 raised to the power 210 mod 6, right? So we need to find an integer x such that x is congruent to 1 mod 2, because when divided by 2 it leaves a remainder of 1, and when divided by 3 leaves a remainder of 0, and x is congruent to 0 mod 3. So I'll just put these in italics. You can see the equations. Now, by CRT, such an x will be unique modulo 2 times 3, which is equal to 6. So by Chinese remainder theorem, this x will be unique modulo 6. So we sort of know that will be unique modulo 2 times 3, which is equal to 6. So what this essentially means is that uh, since so basically what we have is that if we find an integer x such that x is 1 mod 2 and x is 0 mod 3, uh, then we also sort of know that 9 and 9 raised to the power 210 also satisfies these two properties, right? That 9 raised to the power 210 is congruent to 1 mod 2 and is congruent to 0 mod 3. So x also satisfies these properties, and 9 raised to the power 210 also satisfies these properties. And since we want to find out the solution modulo 6 here, so when we are taking modulo 6, we know that the solution will be unique by Chinese remainder theorem. So what this essentially means is that x will be nothing but x will be 9 raised to the power 210 mod 6. So I hope this is sort of clear to everyone that we need to, if we find an integer x, like we need to, instead of this, if we write this, if we find an integer x such that x is congruent to 1 mod 2 and x is congruent to 0 mod 3, this x will be unique modulo 6. And since 9 raised to the power 210 also satisfies the above two congruence equalities, the above two modulo equalities. Hence, uh, x is actually congruent to 9 raised to the power 210 mod 6. So what I essentially mean to say is that if we find uh, to find this 9 raised to the power 210 mod 6, we just need to find out an x such that x is congruent to 1 mod 2 and x is congruent to 0 mod 3. If we find this x, then this will be actually the answer to 9 raised to the power 210 mod 6 also. So finding such an x. So how do we find? So if I find an integer x which satisfies these two inequalities, then I'm sort of done. Then we have that x is congruent to 910 mod 6, 210 mod 6. We know this by Chinese remainder theorem. Now, how do we find such an x? For this, we use this second part of the Chinese remainder theorem. So which claims that x is actually equal to this quantity, y1 m1 a1 plus y2 m2 a2 and so on. So uh, maybe to be just a bit more clear, like here we have m1 equals to 2 because the first number, like the two inequalities are, note that the two inequalities here are uh, this x is congruent to 1 mod 2 and 0 mod 3. So a1 is 1 and m1 is 2. Similarly, a2 is 0 and m2 is 3. This a1 is 1, m1 is 2, a2 is 0 and m2 is 3. And we have this capital M equals to 2 times 3, which is 6. So now to find out this value of x, we just need to define these variables. Like this is just a formula based thing. And so yeah, we just need to plug in the values of m1, a1 and so on. So yeah, so just plugging in these values, finding such an x, we use the second part of CRT. That is, so basically m1 equals to 2. We know that the a1 here was 1 and m1 was 2. Similarly, a2 here was 0 and m2 was 3. a2 here was 0 and m2 was actually equal to 3. So we have these four variables, and then we define these values capital mk, right? So, and we have this capital M also. So capital M is equals to m1 times m2, which is equals to 2 times 3, which is equals to 6. Similarly, capital M1 is nothing but capital M divided by small m1, which will be. So these are just formula based stuff. So I'm just plugging in these values of a2 equals to 0, m2 equal to 3, a1 equal to 1, and m1 equal to 2 in all of this. And we'll have this x as the final solution. So I'm not doing anything fancy. I'm just, maybe you can try these calculations yourself also, but I'm just following along with the calculations and nothing else. So this will be equal to 6 divided by 2, which is equals to 3. Similarly, capital M2 will be equals to capital M divided by M2, which will be 6 divided by 3, which will be equal to 2. So we have these capital M1s and capital M2s calculated. We have this capital M also. Now, what else do we need to find? We have these capital M1, we have this small a1, a2, a3s, capital M1, capital M2s. Now we need to find this y case, like small y1 and small y2, essentially. So y1 is nothing but multiplicative inverse of m1 modulo small m1. So I'll just write it down here. So y1 is nothing but multiplicative inverse of capital M1 with respect to small m1. which is equal to, or not with respect to, let's say mod small m1. Yeah, it was small m. So which will be nothing but a multiplicative inverse of capital M1. Capital M1 is nothing but 3 modulo small m1. Small m1 was equal to 2. So y1 is nothing but multiplicative inverse of 3 modulo 2. So we need to find a number y1 such that 3 times y1. So what this essentially means is that this implies that 3 times y1 should be actually congruent to 1 mod 2. This is the definition of multiplicative inverse, right? I'm hoping you guys must remember this from the lectures. So multiplicative inverse of 3 modulo 2. So this will be equal to y1. So what this essentially means is that when 3 is multiplied by this y1, we get a value of 1 modulo 2. So I hope this is something which is clear to everyone. So we sort of need to find out the value of y1 in this, right? And we can sort of directly see here also that y1 equals to 1 will satisfy this value. Like if we put y1 equal to 1, we'll just get 3, and 3 when divided by 2 leaves a remainder of 1 only. So y1 equals to 3, y1 equals to 1 will work here. Uh, but like here we were able to directly see, but in general, if you want to find out what's the multiplicative inverse, here it was easy to see. But in general, if it is not easy to see, then you will have to go through the procedure which was described in the lectures of how to find multiplicative inverse using extended Euclidean algorithm. So this was also in this week's lectures. Uh, this like how to find out multiplicative inverse of a number. So you can either use that procedure, or like you can just say here by observation that we have y1 equals to 1. Okay, so someone has joined. So hello Jitesh. So I believe you have just joined the session. So this session I was just like I started out with the first problem. So this session is on like number theory you must know. So I was just describing some questions related to Chinese remainder theorem and formats little here. So yeah. So this is the first question which I am discussing. So uh, you can maybe look at what I'm discussing, and if if you have any doubt in what I have written so far, then maybe you can ask me via chat. I'll try to explain it from the start again. So we are sort of doing this question like we need to find the 9 raised to power 210 modulo 6. I'm just at the first part itself right now. So yeah. So we've obtained y1 equals to 1 here. Similarly, y2 will be nothing but as described earlier, y2 will be nothing but multiplicative inverse of m2 modulo m2 modulo small m2. And what was the value of m2? M2 was equals to 2. And so I'll just put in the value. These variables here, let me just. M2 was nothing but equal to 2, and small m2 was nothing but equal to 3. So this implies, so basically we need to find multiplicative inverse of 2 modulo 3. And so this implies we need to find out y2 such that 2y2 is congruent to 1 mod 3. And we can easily see again here, either you can apply the whole extended Euclidean GCD to find out the multiplicative inverse, or you can just see that y2 equal to 2 will satisfy, because if we put y2 equal to 2, this side will be 4, and 4 is 1 mod 3 actually. So from here we'll get y2 equals to 2. Okay. So now we are sort of done. So we have obtained this value of y2, we have obtained y1, we have obtained m2, we have obtained m1, we have this a1, and we have this a2. Then what's the value of x? X is nothing but y1, m1, a1 plus y2, m2, a2 till yn, mn, an. And here n equals to 2 only. So x is nothing but x is equals to y1, m1, a1 plus y2, m2, a2, which will be nothing but equal to just plugging in these values, plugging in y1 equals to 1. 1 times capital M1 will be 3 times A1, which is equals to 1, plus this y2 will be nothing but 2. Then this capital M2 will be equal to 2 again, and this small a2 is equal to 0. So this is the value of x, and like this 2 times 2 times 0 is 0, and this gives me 1 times 3 times 1 is 3. So x is nothing but actually equal to 3. So what we essentially obtain is x equals to 3. And so essentially what we have sort of obtained is for this set of equations, x equals to 1 mod 2 and x equals to 0 mod 3, we have x equal to 3 as a solution. And this is a unique solution with respect to capital M, which was like equal to 2 times 3, which is 6. So from this, we can sort of claim that, like as I said earlier, that 9 raised to power 210 mod 6 will also be equal to this x mod 6 only. So yeah. So if we find any x which satisfies these two inequalities, if any x satisfies these two equalities, then that x is unique modulo 6. And what does that mean? That means that x mod 6 will be essentially equal to this 910 mod 6 also. And we have x equals to 3 here, and 3 mod 6 is actually equal to 3 only. So this 9 to the power 210 mod 6 will actually be equal to 3 only. So I'll just write it down. Hence, maybe I'll just put this equality again. As x mod 6 is equals to 910 mod 6. Hence, 9 raised to the power 210 mod 6 is actually equal to 3 mod 6, because x is equals to 3 here we have obtained, and which is actually equal to 3. So we obtain that this 9 raised to the power 210 mod 6 is actually equal to 3. Yeah. So this is the solution. So this 9 raised to the power 210 mod 6 will actually match to this 3 here. So note that even though this may have looked like a long procedure, like we have found out this y1, m1, m2, and we applied the formula and reasoning and so on, but the overall idea is very simple here. So the overall idea is just find out the prime. If this is a composite number, then just find out its prime factorization. And after finding out its prime factorization, here we found out as 6 equals to 2 times 3. So we just find out the value of 9 raised to the power 210 first when divide by 2, then divide by 3. And we found out the remainders here. And then we just found out the any x which satisfies these two inequalities, like not just this 9 raised to power 210, but we just sort of wrote this as an modulo equality instead. Another equality that x is 1 mod 2 and x is 0 mod 3. And we found out using Chinese remainder theorem the value of x by this y1 m1 a1 plus y2 m2 a2. And then we just found out that 9 to the power 210 mod 6 will be nothing but actually equal to this x mod 6 itself. So the main steps were just factorizing and then finding out the modulo for the unique factors and then writing it out as these modular equalities and then just straight up deriving these variables and applying this formula and straight away. So the part here which I was writing was just to describe the intuition of why we are doing stuff, but the actual stuff which needs to be done is quite simple. So I hope everyone understands this. So yeah. So by this we get 9 raised to the power 210 mod 6 is actually equal to 3. So now let's come to row 2 then. So row 2 is 5. So this was application of Chinese remainder theorem. The second and third rows will be simpler, I believe. So row 2 now wants us to find out 5 raised to the power 300 mod 7. 5 raised to the power 300 mod 7. And this is sort of easy. Maybe I'll just write this as to find. This is relatively easy because we see that this 7 here is a prime number actually. And since 7 is a prime, we can just apply directly the Fermat's Little theorem. And how will this help us? Maybe we can just see. So by Fermat's Little theorem, we have that 5 raised to the power 6 will be congruent to 1 mod 7. I hope this is clear to everyone. This is just the application of Fermat's Little theorem. And since 5 raised to the power 6 is congruent to 1 mod 7, this implies what this implies is that if we need to find out something like 5 raised to the power 300, right? So on both these sides, if I raise to the power, let's say 50, then I'll raise to the power 50 here also. And we can easily see that this side will give me 5 raised to the power 300 and 1 raised to the power 50 will still be 1. So what this implies is that 5 raised to the power 300 is essentially is congruent to 1 mod 7, which is equals to 1. So this implies that 5 raised to the power 300 mod 7 will be nothing but equal to 1. So this was a pretty simple one because we just applied Fermat's last theorem and raised to the power 50 on both sides. So yeah. Okay, now let's come to row 3 then. And what do we need to find in row 3? So in row 3, we need to find 6 raised to the power 9 raised to the power 10. Okay, so this is a bit tricky. Mod 7. So we need to find 6 raised to the power 9 raised to the power 10 mod 7. 9. So I don't believe we can do a superscript again. So I'll just write it as this. Sorry for that. So yeah. So the notation here is this 6 raised to the power 9, and this symbol is for, like, let's say upward arrow is for power again. So 6 raised to the power 9 raised to the power 10 mod 7. Right. So hint here given is basically we first find 9 raised to the power mod 9 raised to the 10 mod 6, and then we proceed with this problem. So Note that there are two ways to proceed with this. Maybe I'll just give you guys this. Maybe we can use this method instead. Okay. So to find out this 6 raised to the power 9 raised to the power 10 mod 7, so we again have something like a mod 7 here, right? So we can again apply something like Fermat's little theorem. Like here we applied Fermat's little theorem and we wrote 5 raised to the power 6 as 1 mod 7, and then we raised both powers to something and we were able to solve. Now we don't know like on how till how much power do we need to raise. Like we sort of know that by Fermat's little theorem that like we can write at least this much, right? That by Fermat's little theorem, we have that 6 raised to the power 6 will actually be equals to 1 mod 7. But now I don't know till how much power should I raise this 6? Like by how much power should I raise this? So that will I ever be able to obtain this value 9 raised to the power 10? Or will I be able to obtain something around this? So the idea here is to like what the hint says, we first find 9 raised to the power 10 mod 6 first. So first we find 9 raised to the power 10 mod 6. And what will this value actually be equal to? This value is something which can again be found out using this Chinese remainder theorem stuff, like because 6 is a composite number, so we just divide it into prime factorization 2 and 3. So essentially, I'm not going to go through these all calculations, but you will see that here also we'll obtain that this 9 raised to the power 10 mod 6 will also be equal to 3 only. Because you can see that when I write the 6 as 2 times 3, then when 9 raised to the power 10 is divided by 2, it will leave a remainder of 1. Like here we had 1 mod 2. And when this 9 raised to the power 10 is divided by 3, we'll again have a remainder of 0, which is 0 mod 3. So the x will remain actually the same. Like the x will satisfy again 1 mod 2 and 0 mod 3. And so finally we'll obtain the same x, which is equal to 3. So using CRT and similar to row 1, similar to done in row 1, we get similar to row 1, we get 9 raised to the power mod 6 is actually equal to 3. So what this essentially means is that this 9 raised to the power 10 can actually be written as what this essentially means that when this 9 raised to the power 10 is divided by 6, it leaves a remainder of 3. So hence we can write 9 raised to the power 10 is equals to 6 times some quotient plus a remainder of 3, where q is an integer. Q is a positive integer, right? Because 9 raised to the power 10 mod 6 equals to 3 implies, maybe we can just say this implies that 9 raised to the power 10 when divided by 6 leaves a remainder of 3. So we get the 9 raised to the power 10 can be written as 6q plus 3. So what we essentially know is that earlier what we just knew was that by Fermat's little theorem, the 6 raised to the power 6 is actually 1 mod 7. But in the problem, we had 6 raised to the power 9 raised to the power 10. And we did not know by how much power should we raise both of these sides to obtain something which is close to this. Like here we knew that we can raise to the power 50 on both sides and we'll obtain our answer. Like we'll obtain 5 raised to the power 300 on left side. But we did not know here on by how much power should we raise. So from here we get an idea that if we raise both sides to a power of q, we don't know what this q is, but let's just say there was this q. then we will have a very nice property, as you see. So if we raise both sides to the power q, we'll have that. Maybe I should write this. Okay, maybe I guess this is okay here. So so 6 raised to the power 6 implies that, like what we did previously, uh, we'll just raise both sides to the power of q here. So 6 raised to the power 6 whole raised to the power q will be congruent to 1 raised to the power q mod 7. And what this will give us is, this will give us 6 raised to the power 6q is congruent to 1 mod 7, because 1 raised to power anything is 1 itself. So still, since we did not know q, so we are still not relieved, because we need to find out this quantity 9 raised to power 10 and not actually the 6 raised to power 6. We need to find something like 6 raised to the power 9 raised to the power 10. So now what we can do is, we know that we can write 9 raised to the power 10 as 6q plus 3. So we have covered the 6q part. We just need this 3 part more. And how can we do? We can just multiply 6 cube on both sides. So this implies that 6 raised to the power 6q plus 3 is actually congruent to, we just multiplied 6 cube on both sides, mod 7. And we know that the 6 raised to the power 6q plus 3, the 6q plus 3 is actually equal to 9 raised to the power 10. So this can be replaced by 9 raised to the power 10. So what this implies is that the 6q plus 3 is actually equal to 9 raised to the power 10. So we can actually write this as 6 raised to the power 9 raised to the power 10 is actually congruent to 6q mod 7. And so we essentially need to find out something. So to find out the 6 raised to the power 9 raised to the power 10 mod 7, we just need to find 6q mod 7. So hence 6 raised to the power 9 raised to the power 10 mod 7 is equal to 6q mod 7, which is equals to 216 mod 7. And like, what is 216? So you can just directly see also that when this 6 is divided by 7, it leaves a remainder of -1. And -1 raised to the power 3 is again -1 itself. So this will give us 6 raised to the power 3 mod 7 will give us -1. And -1 is essentially equal to 6 only. So maybe I can just write it here directly, which is equals to 6. Yeah. So you could have done this directly in the starting also. So we obtain the, so first of all, like, we obtain the value as 6. So we obtain that 6 raised to the power 9 raised to the power 10 mod 7 is actually equal to 6. So this was one way to do this, like finding out this 9 raised to the power 10 mod 6 using CRT, and then raising both sides to the power q and finding it like that. One smarter way here, like just for this problem, is you can see that 6 is actually equal to -1 mod 7, right? 6 is actually congruent to -1 mod 7. So 6 raised to the power 9 raised to the power 10 is nothing but -1 raised to the power 9 raised to the power 10. And since 9 raised to the power 10 is actually an odd number, so this value is nothing but -1 raised to the power odd number mod 7. And -1 raised to the power odd number is -1 itself. So this is nothing but -1 mod 7, which will give me the answer 6 directly. So instead of going through all these procedures and finding out that 6 raised to the power 9 raised to the power 10 is actually equal to 6q mod 7, you could have just written this as -1 mod 7. So I'll just mention this. Like, this is an easier method for this question, a very simpler method, but I want to discuss this method because this procedure might be useful for other questions. When suppose this value was not 6 and instead 5. So you could not write it as -1, but it would be -2 raised to the power something. And that won't be easy to find. So alternate method. So alternate method is something like 6 raised to the power mod 7 is nothing but -1. Maybe I should just copy this first. I can replace this 6 by -1 instead because 6 is -1 mod 7. And since -1 raised to the power this is -1 raised to the power odd number is an odd number. So this will be nothing but -1 mod 7, which is equals to 6. So in alternate method, you can do this in one line. Here it took a lot of lines. But this alternate method is very specific and could just be applied to this question because of the special structure present here. So yeah. So yeah. So that's how we obtain this equals to 6. So yeah. So we are done. So row 1 had an answer of 3, row 2 had an answer of 1, and row 3 had an answer of 6. And we need to find out matching only. So it's since matching question. So row 1 had an answer 3. So 1 will be matched to C. Row 2 had an answer of 1. So second will be matched to B. And this 3 will be matched to A. So 1C, 2B, 3A. Maybe I'll just write down. So yeah, this is the correct answer. Okay. So now we come to the second question then. So maybe I'll just put the whole question on the same page. Okay. So second question says that we are given that x raised to the power p1 is actually equal to x mod p2. Similarly, x raised to the power p2 is congruent to x mod p1. Note that I think these are typo here. These are not equality symbols, but rather congruency symbols. So this is not actually equal to, but rather congruent to. So x to the power p1 is congruent to x modulo p2. X to the power p2 is congruent to x mod p1, where p1 and p2 are prime. And now we want to choose the correct statements out of the among the following. So note that I don't think we'll be needing this sort of hint here in this problem. So the options are x to the power p1 p2 is equal to x mod p1, x to the power p1 p2 is congruent to x mod p2, or x to the power p1 p2 is congruent to x mod p1 p2, and something like that. So uh, first of all, we see that p1 need not be equal to p2 here. Like there can be instances where p1 is not equal to p2, but these sort of things are satisfied. I think it's easy to see here because there is a modulo inequality. So yeah. So first of all, P1 will not be equal to P2, and you can sort of try it yourself. In what cases will this be the case? So let's just ignore that for now. So uh, let's just consider this the first inequality, which is x raised to the power P1. The first equality given to us, which is x raised to the power P1. Okay, is, so again I'm using this as a congruent symbol. So x mod p2, this is given to us. Now what does this imply? If we raise both powers by the factor of p2, you'll see why I'm doing this. So if we raise both sides by a power of p2, we'll get something like x raised to the power p1 whole raised to the power p2 will actually be congruent to x raised to the power p2, because we have raised powers of p2 on both sides, and this will be mod p2. And we sort of, so this will be nothing but x raised to the power p1 times p2, and this will be x raised to the power p2 mod p2. And what do we know about this value? You can see from Fermat's little theorem that x raised to the power p2 minus 1 will actually be equal to 1 mod p2. So this will be nothing but actually x mod p2. So what I'm claiming is this value will actually be equal to x mod p2. And why is this? By Fermat's little theorem. So what we actually get is x raised to the power p1 p2 is actually congruent to x mod p2. Hence, x raised to the power p1 p2 is actually congruent to x mod p2. Similarly, we'll also get we first started off with x to the power p1 is congruent to x mod p2. If we start off by the second equality where x raised to the power p2 is actually equal to x mod p1 and raised to the power p1 on both sides, then we'll again get something like, x raised to the power p1 p2 is congruent to x mod p1. So we got this option, and in similar manner you can show this also by just raising this side to the power of this equality to the power of p1. So what we essentially get is that we get this option A here, which is x to the power p1 p2 is x mod p1. We get option B, which is x to the power p1 p2 is x mod p2. And by Chinese remainder theorem, so note that p1 and p2 can be equal or they cannot be equal, right? So how do I put this claim? Let me just think. So first of all, this sort of thing is always clear to us that we always get these options, right? We'll always get these options A and B here. And now what we do is, so these two options are always correct, that x raised to power p1 p2 will always be equal to x mod p1. Similarly, x raised to power p1 p2 will always be equal to x mod p2. But now we have these C and D options also, right? Which are x to the power p1 p2 is actually equal to x mod p1 p2. And similarly, the other option which says p1 equals to p2. So what we actually want to sort of show here is, how do I put this? So what I'm actually claiming is, yeah, we can maybe use this hint instead. Like, so if we have something like this, that x raised to power p1 p2 is x mod p2, and similarly x raised to power p1 p2 is actually x mod p1. So by this, what can we write? This implies that x raised to the power p1 p2 minus x. Okay, maybe I should not write here, but instead here. Like we obtained that x raised to power p1 p2 is congruent to x mod p2. What this means is that when this quantity, uh, like we can write it as this also, right? That x raised to the power p1 p2 minus x is divisible by P2. So what this essentially means is that this quantity x raised to the power p1 p2 minus x is equal to p2 times some number, let's say q1, like p2 multiplied by q1, where q1 is a positive integer, right? So we have written x raised to power p1 p2 minus x as p2 multiplied by a number q1. And similarly, we also obtain that x raised to power p1 p2 is actually congruent to x mod p1. So similar arguments can be applied here also. And what we'll get is this is divisible by p1. And what this means is that this will essentially be p1. And I'll name this number q2 instead, where q2 is a positive integer. So note that this q1 and q2 need not be equal, obviously. But these are equal, right? This x raised to power p1 p2 minus x is equal on both sides. So what this essentially means is that we can write this x raised to the power p1 p2 minus x as either this p2 times q1 or p1 times q2. So what we essentially state is that I should write like this. Hence, p2 times q1 is actually equal to x raised to the power p1 p2 minus x, which is p1 times q2. So this implies that p2 times q1 is actually equal to p1 times q2. So you might get confused, why am I doing all of this stuff? So like, yeah, this can get a bit confusing, but just bear with me, guys. So what I essentially wanted to say was this p1 was a prime number given to us. This p2 was a prime number given to us. And we have established that there exists some positive integers q1 and q2 such that this p1 times q2 is actually equal to p2 times q1. And now from this, we can use the hint given to us. The hint says essentially that if AP is equals to BQ, where P and Q are prime. So note that here P1 and P2 are prime. So this A and B are replaced by Q1 and Q2 instead. Then we can sort of write A equals to K times Q and B equals to K times P. So the proof of this hint is quite easy to see. You guys can do it yourself also. That if AP is equal to BQ and P and Q are prime here. So if we divide both sides by P, then this side should leave a remainder 0. AP is divisible by P. Similarly, B times Q should also be divisible by P. But since Q is not divisible by P, since Q is prime and different from P, then B should be divisible by P. Right? So what this essentially means is that we can write A equals to K times Q, and B was divisible by P, so B can be written as K times P. So what this essentially means is that similarly now, using the hint given in the question, we can say that. So what do we say here? Here P1 and P2 were prime. So when this side is divisible by P2, this side should also be divisible by P2. So if this side is divisible by P2, then we sort of, so maybe what should I do is maybe in the start of the answer, let's just assume that P1 is not equal to P2. Because it can create some problems, because this hint is only true if P and Q are not equal. If P and Q are actually equal, then this sort of claim can cause some problems. So I'm a bit confused myself, but yeah, let's just assume for now that uh, P1 and P2 are not equal. Because if they were equal, then writing something like this won't be an easy task. Mm, P times P minus 1 will be equals to. Let me just think for a minute, guys. Okay, for now, let's just assume that P1 and P2 are not equal. And let me just crop this option, maybe just remove this option D here so that it's a bit easier to follow. Like otherwise it can get a bit confusing because this sort of hint, as you can see, is only true when P and Q are not equal because if P and Q were equal, then we'll just have P and Q will cancel and A will actually be equal to B always. And this need not be the case that A equals to KQ and B equals to KP. So yeah, so that's why let's just not consider something like that. So yeah. So now using this hint, we can actually say that Q2 is actually equal to some K times P1. This Q2 is actually equal to this Q2 is actually equal to K times P2 because we are dividing by P2 on both sides. So we can write this Q2 as K times P2. And similarly, we can write Q1 as K times P1. And now how does this help us? This may seem very arbitrary, like why are we using this hint and why are we doing something like this? So this will help us because now we can replace here, like let's say we had this Q2 as K times P2, right? So we can write here Q2 as something like K times P2, and we'll have this as K times P1 times P2. So let me just put it this way as is P times Q2. Now we can put the value of Q2 as this K times P2, and what we'll get is we'll instead put this Q2 as K times P2, and what we'll get is essentially that x raised to power P1 P2 minus x is actually divisible by P1 times P2 also because this K is an integer. So x raised to power P1 P1 P2 minus x is actually divisible by P1 times P2. So I hope this is clear, like why is this the case that like we had something like P1 times P2 in this factor. So that's why this is divisible by P1 times P2. And what does this leave us with? This implies that x raised to power P1 P2 P1 P2 is essentially equal to x mod P1 P2. So x raised to the power P1 P2 is essentially congruent to x mod P1 P2. Like this statement and this statement are actually equivalent. So yeah. So essentially all these three options are correct. Like x mod P1, x mod P2, x mod P1 P2. So hence option A, B, and C are correct. So yeah. we had assumed that P1 and P2 are not equal. To just like summarize what we did in this question, we assume P1 and P2 are not equal. Then we wrote x raised to power P1 P2 as x mod P2, applied the Fermat's little theorem. Similarly, we did this again, and then we wrote x raised to power P1 P1 P2 minus x as something like P1 times Q2, and the other one as P2 times Q1. And then we just equated these two quantities. And using the hint, we said Q2 is something like K times P2 and Q1 is something like K times P1. We just substituted the value of Q2 here and we obtained that this quantity is actually divisible by P1, P2. So yeah, this is the overview of the question. Okay, so I think since we are running a bit out of time, maybe I can, maybe I'll just reduce the question. Like I'll not discuss maybe all the questions. Yeah. Okay, so we had discussed the second question, right? So then now first I'll change the order of the question which I'll be discussing. So I would like to discuss this question, this fourth question first, instead of this third question now. Let me just put this on the next page. So this is the fourth question, which says that so note that this fourth question is okay. So the fourth question says that select the correct solutions for x for the equation x raised to the power 86 is equal to 6 mod 29. Right. So we need to find out the possible values of x which satisfy this, that x raised to the power. So to find solutions for x raised to the power 86. So note that this is again not an equality symbol, but rather congruence symbol. There's a typo here. So this is congruent to 6 mod 29. So we need something, we need to find solutions for this. Right. So note that first of all, what we can say is you can see that 29 is a prime. And we sort of know like if x satisfies this equation, like if x satisfies that x raised to the power 86 is 6 mod 29, then we can be sure that x will not actually be, that we can be sure that x will be co-prime to 29. Like what I'm trying to do, okay, maybe I'll just give you the first high level idea first. So this 29 is this 29 is a prime number, right? And when we have something like a mod of prime number, then we generally refer to Fermat's little theorem to proceed further in the question. But to apply the Fermat's little theorem, we first need that this to apply Fermat's little theorem, we need this x to be co-prime to 29, right? If x was not co-prime to 29, then we can't apply like Fermat's little theorem. But we sort of, so we first need to see whether x is co-prime to 29 or not. And we can see that x is indeed co-prime to 29 because it satisfies this equation. And if x was not co-prime, like suppose, so we can easily see that x is co-prime to 29. And why is this the case? If not, then x is actually congruent to, if x is not co-prime, then actually x is divisible by 29. So then actually x is equals to 0, x is congruent to 0 mod 29, which will imply that x raised to the power 86 is actually congruent to 0 mod 29, which is a contradiction. Which is a contradiction. So that's why x is co-prime to 29. So as x is co-prime to 29, hence we can, hence by Fermat's little theorem, we can say that what can we say? X raised to the power 28 is actually congruent to 1 mod 29. This is the format's little theorem, right? And since we have this x raised to the power 86, so we sort of round it to the closest, well, like closest multiple of 28 to 86. So what do I mean by this? We'll just show you guys. So we have that x raised to the power 28 is congruent to 1 mod 29. So if we take the cube on both sides, if we write it as x raised to the power 28 whole raised to the power 3, then this will be congruent to something like a 1 cube mod 1 cube mod 29. So this essentially means that x raised to the power 84 is congruent to uh, 1 mod 29. So what this essentially means is that x square, like what this essentially means is that x raised to the power 84 is congruent to 1 mod 29, and we had something like x raised to the power 86. So multiplying by x square on both sides, so we have that x raised to the power 86 is actually congruent to x square mod 29. So instead of solving this equation, x raised to the power 86 is congruent to 6 mod 29, we actually can replace this x raised to the power 86 by this x square itself. So this implies that we need to find solutions to the equation x square is congruent to 6 mod 29. So instead of finding out x raised to the power 86 is congruent to 6 mod 29, we just need to find out solution to this, to this equation that x square is congruent to 6 mod 29. So, and how do we do this? Like, uh, so note that in general, doing this for arbitrary instances is hard. Like it can take a lot of time. There's no defined procedure till now, like to find, this is called the square root problem. Like find the square root of a number. So essentially we have x square, like we have something like x square is something like a mod b, and then finding out the value of x is something which in modular arithmetic is for which an efficient algorithm is not known. But this question has something like a special property. So what we can sort of do here is one way is just to check all the options, and that's why this is sort of an MCQ based question that you can sort of check all the options here. Like you can just check whether 8 satisfies this congruency or not. Like you can easily check 8 square, like you can easily check the value of 8 square, which is 64, whether 64 leaves a remainder of 6 when divided by 29. Similarly, whether 7 square leaves or whether 28 square leaves or 21 square leaves, and something like that. So something like this can easily be checked. So one way is to proceed like this, that you find out this x square is 6 mod 29 and then just check all the options. Now, just check all the options. Like note that why does this simplifier work? Because finding 8 raised to power 86 would have been difficult, but finding 8 square is easy. So that's why now our problem is a bit simplified and we can now apply all the options. So the smart work was just to reduce this 86 to a square. And after this, no efficient method is known, but some heuristics can be applied, like applying all the options. But I'll discuss another alternate method with you guys just right now. So now just check all the options. Uh, to find which fits the above equality, modulo equality. So yeah. So one way is to check all the options, or alternate method or how can we proceed after this alternately. Like this is just for this question, note that this is just for this specific question. Like an observation based thing, and this is no general procedure. But what I mean to say is, alternately, we can write x square is congruent to 6 mod okay, as x square is congruent to 6 mod 29. We can sort of write it as something like this also, that x square is actually congruent to something like, so if it is congruent to 6 mod 29, then we can add any multiple of 29 to this side, right? So we can sort of write something like 6 plus 29 times 2 mod 29. And this 29 times 2 is 58, and 58 plus 6 gives 64. So what this gives us is that x square is actually congruent to 64 mod 29. And why did I do this? Why did I arrive at 64? Like, what's the problem with 6? Now note that 64 is a perfect square. I can write it as 8 squares. And how will this benefit me? You can just see that by this, I can actually write that x square minus 64 is divisible by 29. So I need to find all x such that x square minus 64 is divisible by 29. And this basically implies like x square, this is x square minus 8 square. So this will be just a minus b times a plus b, which will be x minus 8 times x plus 8 is divisible by 29. So note that earlier I just had to, in this way, we just checked, like earlier we just checked all the options and saw which one fitted and which were not. And we were not sure like whether, like, if we just fit all the options, we don't know like whether the set of options which we have is an exhaustive set. Like, will all the possible solutions be covered in this manner? But in this manner, by this method which I have described, we can sort of arrive at all the possible solutions. And how do we do so? We have sort of described that x minus 8 times x plus 8 is divisible by 29, and we need to find such x. So since 29 is a prime number, then either x minus 8 should be divisible by 29 or x plus 8 should be divisible by 29. This implies that x minus 8 is divisible by 29. Maybe I should write like this. Hence, either x minus 8 is divisible by 29, which implies x is something like x is 8 mod 29, or like I have written this either or here. I should write these both in cap. Or x plus 8 is divisible by 29, which implies that x is actually minus, x is congruent to minus 8 mod 29, which will be nothing but actually 21 mod 29. Like minus 8 is nothing but 1. So yeah. So in this manner, we have sort of obtained, like this is an either or, so we have sort of exhausted all the possible cases. Like here in this method, we just checked all the possible options and we just checked which of the options satisfy this equality. And then we just said these are the correct answers. But if we were not given these options and we want to find out all the possible solutions to this equation, then we need to proceed in this manner, like write 6 instead as something like a perfect square. So this is sort of an heuristic based argument. Like here we wrote 6 instead of 6, we converted it into a perfect square, and then we sort of divided into factors and so on. So note that this is in no way a general method, because here we were just lucky that we were able to obtain a perfect square by applying 29 times 2 plus 6. So yeah. So in this, generally, like this is not a general method, but a specific method for this question. I just wanted to show you guys this also. So So this is the exhaustive set of solutions, that x is 8 mod 29 and x is 21 mod 29. So these are the two values of x which will be the correct solutions. So option A is 8 mod 29 and option D is 21 mod 29. So option A and D are correct. Hence, options A, comma D are correct. So yeah. Okay, so we have this fourth question done. Mm, maybe the third question. So third question is also sort of easy. Maybe I'll just describe you the high level steps, and because this is just a question which is directly based out of lecture. So again, we need to sort of solve the following, match the following regarding the equation 79x is equals to 4 mod 624. So we are given that 79x is equals to uh, 4 mod 624, and we sort of need to find out the something like value of x. We also need to find out 79. So we also need to find out 79 inverse. So let's just solve it row by row. So row one states that we need to find 79 inverse. And like since this question is whole based on modulo 624, so we sort of need to find 79 inverse mod 624. Like the high level idea, what I'm trying to claim is so this problem on a high level, what it is trying to do is it is making us solve this equation that 79x is equal to 4 mod 624. And to solve this, we can sort of, since 79 and 624, you can see are co-prime. So what we can do is we can just multiply 79 inverse on both sides. So we'll get the value of x then equals to, we'll then get x as congruent to 79 inverse multiplied by 4 mod 624. So for this question, first we'll need to find out the value of 79 inverse mod 624. Then we'll sort of need to multiply it by 4 and take mod 624, and then we'll get from that we'll get the value for x. So to find 79 inverse mod 624, so for this, this had been discussed in the lectures that we can do this using extended Euclid's algorithm. Like, try it yourself. This is sort of a try it yourself part because this is straight out of lectures. Like, this is nothing new. So what I'll instead do is I'll just mention you guys like what we'll obtain from this. We'll get that one is so what do we try to do in extended Euclidean algorithm? Like we try to write one as multiple of this 79, the number which we are trying to find inverse of, and the number by which we are taking modulo. So we'll get something like 1 is equal to 79 times 79 minus 10 times 624. So note that these calculations are in no way like straightforward. Like you need to apply this extended Euclid's algorithm to obtain these coefficients. But I just sort of already have had these at hand. I had solved it beforehand. So this is what you get. That we get 1 is equals to 79 times 79 minus 10 times 64. And these coefficients are called Bezout's coefficient. So the second option says Bezout coefficient. So the Bezout coefficient for 79 is actually 79, and Bezout coefficient for 624 is actually this minus 10. Like this whole, along with the sign, we consider the Bezout's coefficient. So Bezout coefficient of 624 is actually minus 10. So for row 2, maybe I should write it as, yeah. So yeah, and now we need to find also 79 inverse, and you can sort of see from here the 79 inverse is actually to find out the value of 79 inverse, uh, the coefficient is okay. So what I'm trying to say, so we want to find out a number x such that when it is multiplied by 79, it leaves a remainder of 1 when divided by 624. So you can see from here that when we divide both of these sides by 624, we'll obtain something like 79 times 79 mod 624 will be actually equal to 1 mod 624. So when 79 is multiplied by 79, it leaves a remainder of 1 on division by 624. So this is something like I'm describing on a high level only because this is something which has been covered in the lecture and is pretty easy to follow. So what I'm actually trying to claim here is to find out the 79 inverse, we just need to find out the Bezout coefficient of 79 and that will actually be the answer. So the coefficient for 79 is 79 itself. Uh, so we'll actually get that this implies that 79 inverse mod 624 is actually equal to just 79 itself. So this is the answer for the first part. And for row 2, we need to find Bezout coefficient of 624. So as you can see here, the Bezout coefficient was actually minus 10. Coefficient is minus 10. And now let's match row 3. So this is more essentially Euclid algorithm is less of like a thinking process and more of just labor work. So that's why I'm trying to avoid this, because this is very straightforward to follow and you can do this easily and obtain this sort of thing. And after that, everything is easy to follow. And now in row 3, we need to find solution for x. So x is nothing but we can easily see that x is nothing but 79 inverse. Since 79x was equal to 4 mod 624, so we took 79 inverse on this side times 4 mod 624. So this is something which we need to do. And we know that the 79 inverse mod 624 is actually equal to 79 itself. So which is actually we obtain from row 1 that 79 inverse is actually equal to 79 itself. So this can be replaced by 79 itself. So which will be congruent. So this will be congruent to 79 times 4 mod 624. And we'll get this value 79 times 4 equal to 316. So yeah. Okay. So the correct answer is actually maybe I'll just write down the correct answer. So basically row 1 is matched to 79, so which is B. 1 is matched to B. Similarly, 2 is matched to A, which is minus 10, and 3 is matched to C, which is 360. So yeah, this is the correct answer. And like this third question was pretty easy. Like you just need to find out when you find out this sort of equation, like after applying extended Euclid algorithm, after that, all parts are easy. Like this 79 versus just the Bezout coefficient, 624's Bezout coefficient is minus 10, and then x is just equal to 79 inverse times 4. So yeah, everything becomes easy after you are able to write this 1 equals to something like this. And this can be easily done like without using any logic or stuff, just applying this extended Euclid algorithm as it is. So yeah. So that's why we are sort of covered this third question also. So if we have covered first question, second question, third question, fourth question. So now comes the fifth question. Okay, so fifth question is again a similar question to what I have discussed. So we are given x is congruent to, so we are given that uh, x is congruent to 1 mod 3. Similarly, we are also given x is congruent to 4 mod 4, and 4 mod 4 can be just written as 0 mod 4 also. Uh, and we are also given x is congruent to 6 mod 7. And we need to find out least possible. And we sort of need to find out the least possible value for x. To find is essentially like we sort of need to find out these options which are factors, but for knowing the factors of the least possible positive value x, we need to actually find the possible value. To find the least possible positive value of x. Right. So again, this is a pretty straightforward question because you can see that we are given sort of three equalities. We are given three modular equalities. X is 1 mod 3, x is 0 mod 4, and x is 6 mod 7. And then we need to find out the value of x. And this is nothing but a direct application of the Chinese remainder theorem. Here we are given three modular equalities, and we need to sort of just apply, find out these mk's, these yk's, and then find out the value of x. So maybe I'll just do this a bit fast because this is just manual labor, but I just want to show you guys also that how will this be done. So these 3, 4, and 7 are co-prime. That's why CRT can be applied, first of all. So this is a direct application of CRT. And how we'll do? So we are essentially given that this A1 is equal to 1 and M1 is equals to 3. Similarly, we are also given A2 is 0 and M2 is 4. A2 we are given as 0 because 0 mod 4 and M2 as 4. And we are given A3 as 6 and M3 as 7. M3 as 7. Now we'll sort of find out first the value of capital M, which is nothing but M1 times M2 times M3, which is, since we are low on time, I'll just be doing the calculations a bit faster because this is just a this is a manual labor work and not something which is very interesting to follow. So M1 times M2 times M3 will be nothing but 28 times 3, which will be 84. So this will be equal to 84. And now we'll find something like capital M1, which will be something like 84 divided by 3, which will be 28. M2 will be 84 divided by 4, which will be 21. And similarly, we'll obtain M3 as equal to 84 divided by 7, which will be nothing but 12. So we obtain M1, M2, M3, and now we'll need to obtain Y1, Y2, Y3s. So Y1 is nothing but, so as we had described Y1, Y2, Y3 earlier also, I'll just be copying. So Y1 is multiplicative inverse of M1 modulo small m1. So similarly, Y2 will be something like that. of m1. So replacing m1 by 28 and small m1 by 3. So multiplicative inverse of 28 modulo 3. Yeah. And this will be you guys can find it yourself, like this won't be difficult to find. So multiplicative inverse of 28 modulo 3 will be nothing but 1 itself, because 28 times 1 will be 28 and 28 times 1 will be 28 and 28 divided by 3 is 1. So y1 will get as 1. Similarly, for finding y2, maybe I just copy this and change the values. So you guys can calculate this multiplicative inverse yourself, because like I said earlier, it's not too difficult to find. You can just use extended Euclidean GCD, or you can just do this faster. Like if you have a high level intuition, like what will be the value? Like if the values are simple, you can just calculate them easily. So I just calculated this orally because I sort of directly saw that 28 when divided by 3 will leave a remainder of 1 as it is. So multiplicative inverse of capital M2 modulo M2, when this will be M2 was 21 and small m2 was 4. So 21 modulo 4, we need to find multiplicative inverse of 21 modulo 4. And note that this will again be 1 only, because 21 when divided by 4 leaves the remainder 1. So this will also be actually 1 only, the value of y2. And now the value of y3. So the value for y3 will be multiplicative inverse of m3 modulo small m3. So capital M3 was something like a 12 and small m3 was something like a 7. So what's the value of multiplicative inverse of 12 modulo 7? So it will be, I believe, something like a mm, this will be 5, 10, 15. So it will be something like a 3. And how did I do? Because 12 times 3 is 36 and 36 is 107. So we obtain y1 as 1, y2 as 1, y3 as 3. So by CRT, x is equals to, so y1, so maybe I'll just copy this formula. That x is equals to y1 m1 a1 plus y2 m2 a2 plus y3 m3 a3. So, and this will be nothing but putting the values of y1 as 1, capital M1 as capital M1 as 28 and small a1 as 1. Similarly, y2 as 1, capital M2 as 21 and small a2 as 0 and y3 as 3, capital M3 as 12 and small a3 as 6. So this will be one such possible value of x. So this will be something like 28 plus this term will be 0 and this term will be, so this will be something like 28 plus 12 times 3 times 6. So it will be something like uh, 12 times 18. And 12 times 18 is 180 and 36, which is something like 216. Oh, yeah. So this is something like 216, which is equal to basically 216 plus 28 is 244. So note that we obtain one such x as equals to 244. So what we essentially get is so what I just want to point out was, in this Chinese remainder theorem, this x equal to this is one of the solutions. X is y1 m1 a1 till yn mn an is one of the solutions. Note that there will be infinitely many solutions because to this solution of x, to this value of x, if we add any multiple of capital M, which is m1 times m2 times mn, then that will also be a solution to all of these inequalities, all of these equalities. So that's why the theorem states that this system has a unique solution modulo capital M. So modulo this value, there will be a unique solution. But in general, this will have infinite solutions because to this value you can add any multiple of capital M, and that will also satisfy all of these equations. You can easily see because this capital M is like divisible by all of these M1 till Mn's. So adding any multiple will not change these equalities. So we'll sort of say that so basically this set of equalities, which are 1 mod 3, 0 mod 4, and 6 mod 7, are satisfied by x equal to 244. And so they are satisfied by any multiple of 244 plus any multiple of capital M. So maybe I'll just write down x equals to 244 mod 84 is a solution for the given equalities. And note that we need to find the least possible positive value. So there are infinitely many values, but we need to find the least possible positive value such that it is 244 mod 84. Since we need to find the least possible positive value of x, we'll get, so you can just see that we'll get x equals to 244 minus. So we need to sort of subtract. So from this 244, we can subtract any multiple of 84 and it will still be a solution. So we'll need to subtract 84 as many times till the value does not get negative. And it will be something like, so we'll sort of need something like 244 minus 84 times some number k. So the 244 minus 84k remains zero, positive. So you can sort of easily check this yourself that the number will be something like 84 times 3. So we'll get the so we'll get something like 244 minus 84 times 3, and this 84 times 3 will be equal to 81. Okay, maybe it will be 84 times 2, not 84 times 3. So this will be equals to let's say 80, 160, 168. So it will be something like 74, and so this 84 times 2 will be 168, and 244 when it is subtracted, 168 is subtracted from it. So we'll get something like 76, I believe. So 76. So we see that 76 is another solution to so x equal to 76 is also a solution to these three equalities. And note that 76 mod 84 cannot be made more negative because we'll need to subtract a multiple of 84 again. And 76 minus 84 will come out to be minus 8. So we can't do that. So this is the smallest positive value, which is the answer. So as you can see, you can directly see also that 76 satisfies all of these. That 76 when divided by 3 leaves a remainder of 1. 76 is divisible by 4. And 76 when divided by 7 leaves a remainder of 6. So yeah, so this is the least positive value, possible positive value of x, which satisfies the solution. So note that even though, so one mistake which a lot of you guys can make is by CRT, you just apply this and obtain the value of x, and you just say, yeah, this is the value, which is the final answer. But note that in this question, we wanted to find the least positive value. So in this, we can always add or subtract any multiple of capital M. So to find the least positive value, we sort of subtracted the maximum possible multiple of capital M, which was like 84 times 2. So hence 76 is the least possible positive value of x. And since 76 is the least possible value, we need to find out the factors of the least positive value in the question. So 76 is divisible by 2, not divisible by 3, but divisible by 4 and not divisible by 5. So 2 and 4 is the correct answer. Hence, options A and C are correct. So yeah, A option was true, C option was false. Okay, so I hope the overall idea of the solution was clear. So again, we were given these three qualities, modular equalities, and we just applied CRT. After applying CRT directly, we just obtained one solution, but we need to find the least positive solution. So we just subtracted the highest possible multiple of capital M from the solution which we obtained, and that was our final answer. So note that even though the calculations can sometimes get a bit complex, but the high level idea of what we are doing, the solution should be clear to you. And I believe this was clear enough in this. Okay. So, uh, so this is the, okay, so I guess these were the 5 questions which I want to discuss, and I have discussed all of these. So, and we are 10 minutes late also, like the time is currently 8:10. The session was supposed to end at 8 p.m. So I guess in the last 2-3 minutes, in the last 2-3 minutes, maybe Jitesh, if you have any doubts, maybe you can ask me. If you have any doubts in the session, I'll try to answer it. And if there are no doubts, maybe we can close the session. So, okay, so Jitesh, you had a message at 7:07. Sir, after this one, could you please repeat the intuition behind row 1 of this question? So, sorry, I did not see your message earlier. So, what question? So, you were asking for question 1. So, should I explain it now? Or is it clear to you now, Jitesh? Okay, so you want an intuition for the row 1. Okay, so of the question 1. So, okay, so first of all, Jitesh, let me remind you, we have these two central pillars in the number theory, like this Fermat little theorem and this Chinese remainder theorem. So generally, when the number along which we are taking the modulo, like here we had this mod 6, when this number is generally prime, then we sort of use the Fermat's little theorem. And when this number is composite, we have to sometimes refer to the Chinese remainder theorem instead. So here we had this 9 raised to the 200 and mod 6. So 6 is a composite number. So we'll sort of need something like a Chinese remainder theorem instead. So essentially what we do here is, what does Chinese remainder theorem state? It states that if a number x satisfies some of these equalities, modular equalities, that x is congruent to a1 mod m1, a2 mod m2 till an mod mn, then we'll have a unique solution modulo capital M. So this is what the Chinese remainder theorem states. So what we try to do here is, instead of finding this 9 raised to the 210 mod 6 directly, we first of all do prime factorization of 6 as 2 times 3. And then we find out 9 raised to 210 mod 2 and 9 raised to the 210 mod 3. And finding these two values is quite easy. You can see yourself. So we find out that 9 raised to the 210 mod 2 is actually equal to 1, and when mod 3 is actually equal to 0. So 9 raised to the 210 is divided by 2, it leaves a remainder of 1, and when divided by 3, it leaves a remainder of 0. Now, basically, let's find another integer x. Now let's just say we find another integer x such that x is equals to 1 mod 2 and 0 mod 3, like which is the property of 9 raised to the 210 also, that it is 1 mod 2 and when divided by 3 it leaves a remainder of 0. So let's just find another integer x which satisfies these two properties. And now how can we find this number, which has x, which has 1 mod 2 and 0 mod 3? We can find such an x using the second part of theory, like CRT, like what I did just here in the last question also, like uh, using this formula which is given to us, like in this Chinese remainder theorem, that x equal to this is the solution y1 m1 a1 till yn mn an. So I find out an x using just these definitions, and just putting in the values. And so from this, I find out such a value of x. Like I get this x as something like, let's say, a 3 here. And now what I want to say was, so how is this related to 9 raised to power 210? So what I did was, first I found out 9 raised to power 210 leaves a remainder of 1 when divided by 2, and when divided by 3 leaves a remainder of 0. Now I took another number x and I said that x is 1 mod 2 and 0 mod 3. But how are these 9 raised to power 210 and this x related? This might be a question which might be popping up in your mind. Like finding this x is easy by using this formula, but how is this x related to 9 raised to power 210 actually? So how is this related? Note that Chinese remainder theorem states that if an x satisfies these values, a1 mod m1, a2 mod m2, and so on, then it will have a unique solution modulo capital M. So what I mean to say here is, so if an x satisfies 1 mod 2 and 0 mod 3, then there will be a unique x modulo 6, because capital M is 6 here, 3 times 2. So it will have a unique solution modulo 6. So what this essentially means is that a 9 raised to power 210 mod 6 will actually be equal to x mod 6. Always. And why is this the case? Because with respect to mod 6, this equation should have a unique solution. And we know that one solution for this equation is x equal to 3. And another solution for this equation is 9 raised to power 210. Because we saw 9 raised to power 210 divided by 2 leaves a remainder of 1 and leaves a remainder of 0 and divided by 3. So we know that this equation has at least two solutions, which are 9 raised to power 210. And the other solution is this 3, which we derive from CRT. And now what we claim is, if we have two solutions, then they both must be unique with respect to modulo 6. So 9 raised to power 210 was a solution and x was a solution where x was equal to 3. So with respect to mod 6, both of these solutions should be equal. So 9 raised to power 210 mod 6 should actually be equal to x mod 6. And from this, we obtain the value of 9 raised to power 210 mod 6 easily, equal to 3. So I hope now the intuition makes a bit more sense, Jitesh. Like, okay, it makes sense. Nice. So you see, like, the main idea is generally like apply CRT when we have composites and apply Fermat's theorem when we have prime. And CRT looks a bit complicated, but overall it's a pretty simple theorem and just calculation based stuff. So yeah. Okay, so if you don't have any doubts, maybe I can stop recording and close the session, since we have also run out of time. So yeah. So okay, so you don't have doubts. Nice. So thanks for joining, everyone. So hope to see you guys next Tuesday, same timing, 6 to 8 p.m. again. So yeah. So till then, goodbye. I'll just be closing the session and you can leave, Jitesh. Thank you.